And the next speaker is Ben Gripaios on generalized symmetries, smooth generalized.
There we go. Okay, I just. That's good. Perfect. Thank you very much. Thank you. So I'd like to describe some work with Oscar Randall Williams. He's a mathematician, and Joe Tooby Smith. The title is Smooth Generalized Symmetries, but I'd like to start with the really big picture, which is our current understanding of quantum field theory. And I'd like to make an analogy between our understanding of QFTs today and our understanding geography, places in the world, in 1459. And I've already given the game away by writing QFTs instead of QFT, because the key idea in this talk will be to think about not just one QFT, or even a family of QFTs parameterized by, say, coupling constants, but to think about all of them all at once. And the idea behind the analogy is this. I chose 1459 because that was the date that this thing was produced. It's the Mappa Mundi in Venice. And what you see, I should stop to say that this map was produced using an annoying medieval version of the mostly plus metric convention, in that it's upside down. But if you look closely, you can see, here we are, upside down at the top of England. You can see that in those days, we understood places, individual places like Southampton, very well. And because we could travel short distances, we understood their local neighborhoods very well. But when it came to the big picture, long distance travel in those days was very difficult. And when it came to the big picture, we didn't know very much at all. We knew one key fact. And the key fact that we knew indirectly is that the places assembled themselves into a world which had the topology of a two-sphere. And that led to an idea that we physicists might call duality. The idea was that you could set out for the Indies, for example, not just by going east, but also by going west. And of course, 30 years later, Columbus set out going west for the Indies, and he discovered that it was not quite as simple as that. There was something in the way. And that something in the way, I probably shouldn't say too much about it in a conference which is so Eurocentric, but I think probably all of us can agree that it was that discovery which ultimately led to the intimate understanding of geography that we have today, epitomized by pictures like this. And the reason I think there's a good analogy with QFT today is that much of that is true. So in quantum field theory today, we understand certain places, free field theories, for example, very, very well. And because we can do perturbation theory, we also understand their local neighborhoods very well. But as soon as we try to go further away, because of strong coupling this time, not long distance travel, things start to get difficult. We have some ideas about duality, about this being the same as this and so on, but we have a very poor global picture. In particular, we most definitely do not know that the space of all QFTs, assemble themselves into the topology of a two-sphere. In fact, they definitely don't. But we do know one small thing, and I think it's the most important thing, and it really is a miracle. The miracle is that quantum field theories really do assemble themselves into a space of some kind. And you might think, and here the analogy is quite bad because it's somehow obvious that things have to form a space. It isn't true. If you take most structured things in mathematics, like groups, vector spaces, whatever you like, if you try to assemble them together into a space, you end up basically throwing away all the information that they contain. And so the miracle here is that you can take quantum field theories and you can assemble them into a space without cheating. That is to say, if I hand you this space, you will be able to take it and reconstruct not only every quantum field theory, but all the information in every one of those quantum field theories. For example, all of the correlation functions. And so that's really, if that's true, it's a big deal. And it is true. And in fact, even more is true. If you take the special case of quantum field theories which are simple in the sense that they're topological quantum field theories, even more of a miracle happens. And the miracle that happens is that those topological quantum field theories assemble themselves into a space that is the simplest kind of space of all. It's a homotopy type. And that's a mathematical theorem, almost, and it goes by the name of the cobordism hypothesis. So, just to make sure that we are all on the same page, let me remind you of what a homotopy type, or let me tell you what a homotopy type is. In topology, we say that two maps are homotopic if you can find a path between them in the space of maps. We say that two spaces are homotopy equivalent if you can find maps going between them whose compositions in both orders are homotopic to the identity maps. And then we'll say that a homotopy type is just an equivalence class of homotopy equivalent spaces. So for example, the real line and the point lie, they correspond to the same homotopy type. So it's really a simple thing. Let me open a parenthesis here to remark that a homotopy type has no notion of smoothness or even continuity. And you can see that already from my example. If a point and a real line are the same thing, there is no notion of open sets and things like that. So they're very, very simple. It's the simplest kind of space there is. And that's both a blessing and a curse for our purpose of studying QFTs in this way. The blessing is that it's really simple. The curse is that it's already clear that there is no way that we're going to be able to describe the full space of non-topological dynamical quantum field theories using just a homotopy type. Because dynamical quantum field theories have coupling constants and you can move smoothly around in that space. And if you have no notion of smoothness in your space of all theories, it isn't going to work. And so for non-topological quantum field theories, we're going to need to make use of a dirty word. And the dirty word, at least a dirty word for physicists, the dirty word for physicists is the sh word. And the sh word, children look away, is sheaf. And it's even worse than that. We're going to have to use a really dirty word, which is something called an infinity sheaf. But that's going to come in the second part of the talk, and so I leave it for now. I close the parenthesis, but I do not stop with the dirty words, because now I want to talk about the cobordism hypothesis, and even to formulate that thing, let alone to prove it, requires me to use a word which for physicists is the dirtiest word of all. It's the C word. And the C word is category. And in fact, again, it's even worse than that. It's infinity category. And if you know what a category is, well, firstly, you shouldn't be in this room, but if you do, an infinity category is something which has not only objects and morphisms, but it has morphisms between morphisms, or two morphisms, and morphisms, and so on, all the way up to infinity. Now, I don't want to say any more about that, except to say why you need it to define the things that go into the cobordism hypothesis. And what you need is you need it to define a quantum field theory. You must now be thinking, this guy is crazy. Why do you need it? Here is a physicist's definition of a quantum field theory. At least the start of it, what you do is this. You assign a number to space-time. And that space-time is usually just something like a d-dimensional sphere. And as it stands, that definition is completely alocal. It has absolutely no notion of locality built into it. And we all believe that locality is one of the sacred principles of physics. And so you have to do more. And of course, a physicist does do more. What a physicist does is say, well, actually, you're not allowed any number. You're only allowed ones which are expressible as path integrals of local actions. And unfortunately, the mathematician is not happy with that because, of course, the notion of path integral is not well defined. So way back in the 80s or so, the mathematicians tried to come up with a definition of quantum field theory which is really rigorous. And the idea they had is to throw away this notion of actions and so on, and to replace it by the idea that instead of just assigning, in your definition of QFT, instead of just assigning data to one closed D-manifold, D-sphere, you assign data not only to all D-manifolds, but D-manifolds with boundary, and D-1 manifolds without boundary. And you must assign that data in a way which is compatible to make everything local. And the nice way to do that, I think this was Atiyah who pointed this out, is to use the language of categories. And it was Lurie who went a step further in the early 2000s and realized, well, it was realized before, but he really exploited the idea that when you try to use this categorical definition, it's the analog of insisting on locality in physics, but only asking for the Hamiltonian to be local, a function of time. Whereas, of course, we field theorists know that really you need the Hamiltonian density to be local. And the fix is to go beyond categories and to ask that QFT is defined by assigning data to all sorts of things. You assign data to points, 1 manifolds with boundary, 2 manifolds with boundaries and corners, all the way up to d dimensions. And another insight of Lurie was that it's actually a good idea to keep going and assign data all the way up to infinity to things like isotopies of d manifolds. I don't want to say what that is. All the way up to infinity. And the reason that's a good idea is that it allows you to incorporate into your definition not only notion of locality, which we all believe, I hope, is a sacred principle of physics, but also one of smoothness. And you might not yet think that smoothness is a sacred principle of physics. By the end of the talk, I hope you will agree with me that it is. Okay, so we're 10 minutes into the talk, and I have not yet said the word generalized symmetry. So what is the connection with generalized symmetry? We said that the cobordism hypothesis tells us that the space of all topological quantum field theories, at least, is a homotopy type. And an important invariant of a homotopy type is its fundamental group. Or rather, its fundamental groups, because you can have a different fundamental group at every point. The fundamental group, or pi1, remember, is you take your base point, you consider loops in it, the set of those up to homotopy, and by concatenating them, you get a multiplication law, and that defines a group. And the cobordism hypothesis, not only does it tell you have a space, it tells you another thing. It tells you that the symmetry group of the QFT, which lives at, say, this point, is the pi1 of the space at that point. It is the fundamental group. You can, however, go further. Anybody in this room who knows what a fundamental group is will probably also know what a higher homotopy group is. And this time, instead of considering loops at a point, you consider 2 spheres at a point, 3 spheres, and so on. The cobordism hypothesis tells you that pi n, for n greater than or equal to 2, corresponds to the n minus 1 form generalized symmetry of the topological theory, which lives at that point. Note that there's a shift in the indexing, n goes to n minus 1. Here's a sanity check. The paper by Seiberg and company that started the ball rolling with generalized symmetries had an argument about moving defects around to say that one form and higher symmetries were abelian. It is a well-known fact that the pi n's, the higher homotopy groups of a homotopy type, are all abelian. So that works out quite nicely. Okay, so this is like a nice correspondence between homotopy groups and generalized symmetries, but there's much more to this than just pretty pictures, because here is a mathematical theorem. The mathematical theorem says that homotopy types are completely classified by the following data. You need to tell me the thing called pi 0, the connected components, the set of connected components. You need to tell me the higher homotopy groups from pi 1 all the way up in principle to infinity. And you need to tell me 2 more things. And the 2 more things are an action of the fundamental group on the higher homotopy groups. And then the remaining thing is something called Postnikov invariants. They're things which live in cohomology groups. And if I give you a space, once I tell you all that, I've told you everything, and that uniquely identifies the space. That's what it means to say they classify things. And that's a mathematical theorem, but it has an immediate application to physics. Because remember, we already said that the symmetries and the generalized symmetries just correspond to the pi 0 and the pi n's. What this theorem says in the language of physics is if I tell you 2 more bits of information, I've not only told you the symmetry of the theory, I've told you the whole theory. In fact, I've not told you the whole theory, I've told you the whole space of topological quantum field theories. If I give you that information, I've told you everything. So what do we say? The slogan is, if you like, that in fact topological quantum field theories are classified by their generalized symmetries. Once I give you the higher form groups and these 2 extra bits of information, I've given you everything. You can construct every single topological quantum field theory once I tell you that information. So how is this theorem useful? Let me just describe 3 applications. One is, of course, that you can try to actually find out what the space is. You can try to classify topological quantum field theories. And the way to do this is to not go for all of them at once, but to break it down into connected components which correspond to, say, the different dimensions of the topological field theories and the different structures that you allow on space-time. If you have fermions, you might want a spin structure on your manifold, and so on. Here's an example, one-dimensional topological quantum field theories. You do a calculation, and again, the cobordism hypothesis, one of the great things about it, it is not just an existence theorem, it's constructive. It tells you how to compute this space. So you do a computation, and you find this is all the information you need to know about all one-dimensional topological field theories. I will tell you that there is a non-negative integers worth of them. That's just the dimension of the Hilbert space, which has to be finite. And then the symmetry group of that theory, of each one, the one which has an m-dimensional Hilbert space, is GLM. Is GLM rather than UM? Because I have not asked for a unitarity structure here. I've just asked for locality. It's very unnatural to ask for unitarity when you have no metric on space, for example. Here's a sanity check. Topological quantum field theory to a physicist, one definition is a thing whose Hamiltonian is 0. If the Hamiltonian is 0, you can do any transformation of the Hilbert space, and it's going to commute with that Hamiltonian 0. Okay, so that's a description of one-dimensional topological field theories. Let's do two-dimensional topological field theories. And I've chosen the simplest case, which is so-called frame theories. Again, the cobordism hypothesis says if you do this calculation, you've done all the other structures at the same time. Now things are a little bit more complicated. Things are a bit more complicated. I have to tell you a pi 0. There's one now for every positive integer. I have to tell you a pi 1, a pi 2, that's like a one-form symmetry group. I have to tell you an action of pi 1 on pi 2, and I have to tell you a Postnikov invariant. And you can do a calculation if you know enough about topology, and that tells you what all of the two-dimensional topological field theories are in dimension 2. This is like an old result of digraph, except now these theories are fully extended. They're fully compatible with locality. So it's not quite the same result, and the answer is not quite the same. You can already see that strange things happen because even though a two-dimensional topological field theory also has 0 Hamiltonian, it's not true that you can do any unitary or linear transformation on the Hilbert space. Because you had to define this thing locally on all two-dimensional manifolds, you're not allowed to do that. You can only permute the basis states, if you like. Okay. I should say that these kind of computations become extremely hard above dimension 2 for a number of reasons. With this classification, you can do real physics. In particular, you can very quickly check claims that other people have made about topological quantum field theories. Here's one again from this original paper by Seiberg and company on generalized symmetries. They gave as an example of a one-form symmetry, they gave the example of two-dimensional gauge theories where you basically integrate out the gauge field. And they said that there are one-form symmetries as well as naught-form symmetries which take the form of some cyclic groups. The actual details don't matter. Once you know the classification, you can see immediately this cannot be the whole story, because the one-form symmetries of topological field theories, they have to be some kind of linear groups. They're like rephasings, but the complexified version of that. And cyclic groups are not the same as those things. And the real story is that the one-form symmetry of these theories is much larger than the one which is described, claimed in the Seiberg and company paper. This is just a subgroup of this much larger group. And it's interesting to see why that happens. It happens because of duality. I've already told you the classification says that there's only a positive integer's worth of two-dimensional topological field theories. So every one corresponds to some positive integer. That means that you could start from your classical actions, you could start with any gauge group you liked, you could start with any one of the possible actions. In fact, you could even start with some theory which had completely different field content. But when you do your path integral, you have to land on one of these m's. And so there are many more theories which are actually equal or equivalent or dual, call it what you like, than you think there are. And that means, in consequence, that the symmetry of any one theory is much larger, because you can do transformations that take you to what look like completely different theories. They're the same one, and so it's a group element. And I refer to that as duality bites. Okay. A second thing you can do, you can classify all topological quantum field theories, you can classify all of their symmetries. We know in physics that you can have symmetries which are not just representations on Hilbert space, but you can have projective things and so on. Wigner produced a famous result saying that with unitarity, the only thing you have are projective and antilinear. Here you can do another computation which tells you what all the possibilities are in the topological case, and you get everything that Wigner found and a few more things besides. And a third thing you can do, with this classification is you can look at anomalies, both gauge and global, of both gauge and global symmetries of these theories. And here's something quite interesting happens, which is that in all the examples which we know about where you have two-dimensional topological field theories with anomalies, 't Hooft anomalies, so we're talking about global symmetries now, you find that they always correspond to a failure to preserve locality. And so this is how it happens. Again, let's go back to the physicist definition of a global symmetry. You just ask for a transformation that leaves a partition function invariant. And again, that is, at least that part of the definition, is completely ignorant of locality. What you really need to do is make a definition of a symmetry as some transformation which preserves all of these assignments of data to all of the ways you can cut up your two-dimensional manifolds. Thank you very much. And when you do that, what you discover is there are lots of things which you think are symmetries, because you can define them like this, but you cannot extend the definition all the way down, and they correspond, in known cases of 't Hooft anomalies, to 't Hooft anomalies. So I think that's a nice insight. The slogan is that 't Hooft anomalies correspond to a failure to respect locality in your definition of a symmetry. And I believe, or at least I suspect, that that is more generally true. Okay, and then for gauge symmetries, you can also ask whether there are gauge anomalies. And again, I don't want to go into the details. Suffice to say that the cobordism hypothesis tells you exactly when you can and you can't gauge the symmetries. So, to sum up this first part of the talk, which is actually most of the talk, for topological field theories, once you make a proper definition, and once you insist upon locality, you get all of this stuff out for free. So now let's ring the changes for the quantum field theories that we're really interested in, namely the ones which are non-topological. And the key point here, and I only really want to make one point, the key point is that now, unlike for the topological case where locality was everything, here you need an extra ingredient which should be elevated to a sacred principle of physics, which is smoothness. And so what do I mean by that? We all learn as undergraduates that you can take any function in physics to be as smooth as you like. And most of the time, as undergraduates at least, we take those functions to be absolutely smooth, infinitely differentiable. But sometimes, like when you have waves going into boundaries and things, you say, well, actually, I'll let them only be once differentiable and things like that. You can take them to be as smooth as you like. And that's why no physicist ever bothers learning analysis. Why is that true? It's just effective field theory. As a physicist, you can only resolve in an experiment down to a certain length scale. I can take any non-smooth function and I can replace it by changes which are below that length scale and turn it into a smooth function. So if you're an undergraduate, you can take functions to be as smooth as you like. Once you graduate and you start to ask questions like what is the space of all quantum field theories, you cannot take functions to be as smooth as you like. Because if you do so, you will double count. You will overcount, you will undercount. Because there will be quantum field theories which look like they're different, but they're not. So you have to make everything smooth, and you have to do it in a uniform way. And so smoothness should be a sacred principle, which is really drummed in to undergraduate physicists. Once you do that, you end up with an analog for quantum field theories of the cobordism hypothesis. At the moment, it exists only in preprint form, but I suspect it's true. It's called the geometric cobordism hypothesis, and it says the space of all QFTs is a space, firstly, but it's a slightly more complicated space in the sense that it's a sheaf. And what that really means is, instead of just having a homotopy type, what you do is you assign a homotopy type to every copy of Rn for every n, and you have to do that again in a compatible way, meaning compatible with smoothness. So it's actually not much more complicated. But as soon as you realize that that's true, you also realize that you are never going to be able to do a classification like we did a classification of homotopy types, because, for example, a manifold makes a smooth space of this type, and we know that it's not possible to classify all manifolds. But you can still do, you can still do many of the things that we did for topological field theories. So I just want to do one example, the simplest example I can think of, and in fact it's the only example where I was able to calculate. And the example is this. You take one-dimensional quantum field theories, along with the data you have before, you have a metric on your space-time, or rather time, because it's one-dimensional. And that means that intervals have a length, that means you can have time evolution, that means you can do quantum mechanics. And so somehow, these theories should correspond to what we think of as quantum mechanics. And indeed, you do the computation, you work out what space you get, And the space corresponds to something which is not quite a manifold, but it's a manifold with an action of a Lie group. And the manifold is, for each n, it's n by n Hermitian matrices, i.e. Hamiltonians. And the Lie group which acts on it is unitary transformations. So you do this computation, and you get exactly what you expect. The space of all possible theories, compatible with locality and smoothness, and I threw in unitarity as well, is just what we think of as a quantum mechanical theory. And here's the important thing about smoothness. Every physicist knows that you can take your Hermitian matrix and you can diagonalize it. And this is telling you somehow that you should not do that. Because if you always diagonalize your Hamiltonian, then the space you produce, which is like n real eigenvalues, but you're allowed to permute them, that's not a smooth manifold anymore. And so if you do that, if you always diagonalize your Hamiltonian, if you do it for one problem, you won't get into trouble. If you study the space of all Hamiltonians and see what happens, you can get into trouble if you can do that. And here's one nice phenomenon which happens, which is an example of an anomaly, which now is not due to a failure of locality, but it's a failure of smoothness. And the example is this. It's It's the simplest physical system there is. You take a spinning electron in a uniform magnetic field. It's a two-state system. It has eigenvalues like this, 1 and minus 1 in some units. You can find symmetries of that system. They're not projective. They're even more complicated than that. You find that you cannot extend those symmetries smoothly to the space of nearby theories. So there's a new kind of anomaly, which is not an anomaly of a theory. It's more like an anomaly of a space of theories. And I think it would be very, very interesting to figure out what the physics of that is. Just like a 't Hooft anomaly, I don't think it's an inconsistency of the theory, but it's telling you something about the theory. And I suspect there's a connection there to very phenomena because you're moving around in the space of theories. So I finished there. The summary of my talk is simply this. I think it's a good idea to not just think about individual quantum field theories or even local families of them, but to really think about the whole space at once. And I hope that by doing so, we can learn some new and interesting things about the global structure of QFT that we didn't know before. Thank you very much.
Thanks, Ben. Questions?
Yeah. Can I ask first?
Okay. Let's start there, yeah.
Yeah, thank you for the very nice talk. Just a short question. I know that for CFTs there are those old papers by Segal with this categorical language. What do you know about the space of CFTs from this perspective?
So the first thing to say there is that indeed for dynamical quantum field theories, it was Segal who started this off. In fact, the first paper was trying to study conformal field theories. It basically went nowhere because it's too hard. This new formalism of thinking about infinity categories rather than categories and everything being smooth, in principle, is the way to solve that problem. However, it is still true that the actual computations are fantastically hard. And so I cannot tell you yet what the space of CFTs is. It's even worse than that because there's a fundamental problem which I'd be happy to explain to you after about how to even define the theories in the first place. Everybody knows that quantum mechanical theories, they live in, there are states in vector spaces, and so the target category, so to speak, of the field theory should be some category of vector spaces. Once you go above dimension 1, nobody knows what the correct target category is. So in a sense, there's not even a point in trying to attempt this calculation until you've decided, and physics should decide, experiment should decide, what the correct target category is. So somehow we have in principle the tools to do it, but we're nowhere near doing it yet.
Thanks.
Okay, thank you. Yeah.
So this talk is very relevant to some of the work that I've been doing with my advisor. So you said that the Corbordism hypothesis can tell you that when can you gauge a particular generalized symmetry or not. So one thing that you didn't talk about in your talks is actually more relevant to the work, and that's non-invertible symmetries, right? And the thing is that right now we were working on something, so you have a non-invertible symmetry, which is actually a rep of some Hopf algebra. And the thing is that you cannot always gauge it, but you can gauge it if you can make a Frobenius algebra out of it from the dual Hopf algebra. So do you know if Corbordism hypothesis says something about gauging non-invertible symmetries?
Yeah. So the answer is it should, but it hasn't yet. There's a version of the cobordism hypothesis, again, which is covered by Lurie, called cobordism with singularities. Mm-hmm. And that is the right thing to do to study non-invertible symmetries. You can go through it and in principle ring the changes. You don't get a space anymore. The point is with non-invertible is that there are morphisms which are not invertible. But you can do all the same things, and indeed, from what you just described, I think it's very likely to be the case that the fact that you have to have extra conditions on the theory, like you just described, to be able to gauge it, can exactly be phrased in this way, that you have, for example, a symmetry which you define in a way which is not fully compatible with locality, and you cannot extend it downwards. And notice, it's not saying you can't gauge it, it's saying there's a problem with the definition of the global symmetry in the first place, and you have a 't Hooft anomaly. And actually, the fact that you can't gauge it is somehow a secondary consideration. But it sounds very much of that flavor.
I see. Thank you.
Thank you very much.